Imagine Earth and Mars sitting side by side at a cosmic roulette table, both waiting to see who gets oceans and who gets dust. Earth won by a hair, literally, a few degrees and a magnetic field away from being as lifeless as our red neighbor. This opening sets the stage for how close we came to being Mars's twin in tragedy, rather than triumph. 4.5 billion years ago, the solar system wasn't the peaceful clockwork we see in textbooks. It was chaos. Rocks the size of continents flying around like cosmic dodgeballs. Newborn planets colliding in what could only be described as interplanetary sumo wrestling. In the middle of this celestial brawl, two worlds began to form, Earth and Mars. Both were rocky, both soaked in molten heat, and both seemed destined for greatness. They were in many ways siblings, born of the same dust, spinning under the same star, and wrapped in the same early chaos. But fate, or physics, depending on how romantic you feel, had other plans. The early solar system didn't hand out habitability like participation trophies. Everything depended on location, timing, and a sprinkle of luck. Too close to the sun, and you'd end up a scorched wasteland like Mercury. Too far, and you'd freeze solid like the outer planets. Earth just happened to settle into the sweet spot, the Goldilocks zone, where water could exist as a liquid. Mars, just one step further out, wasn't so lucky. In cosmic terms, that small distance, barely 50 million miles, made all the difference between blue skies and red deserts. But at the start, no one could have guessed who would win the planetary lottery. Both worlds began hot, molten, and covered in magma oceans that could have melted steel. The early atmosphere was thick with carbon dioxide, methane, and ammonia, a mix that would make any modern environmentalist faint. Volcanic eruptions painted the sky with ash, asteroids crashed down with the enthusiasm of a toddler smashing toys, and lightning storms raged for centuries. Yet somehow, in all this madness, the seeds of habitability were being sown. Think of it like baking bread. Too much heat, and you burn it. Too little, and it never rises. Earth cooled just enough to let its crust form, creating the first continents and basins that would someday hold oceans. Mars cooled faster because it was smaller, which sounds great if you're a planet trying to chill out, but terrible if you want to keep your insides warm enough to power volcanoes and magnetic fields. Mars, in a sense, aged too quickly. It was the planet that peaked in its 20s and has been reminiscing ever since. What's striking is how close Mars came to being our twin. Ancient riverbeds still snake across its surface, frozen reminders of a wetter, warmer past. Scientists have found minerals that can only form in liquid water, suggesting that billions of years ago, Mars had lakes, maybe even shallow seas. Imagine standing on early Mars, watching a salmon-colored sunset over rippling water. It could almost have been Earth, except the dice rolled the other way. Mars's smaller size meant it couldn't hold on to its internal heat, and when that heat faded, so did its magnetic field. Without that protective bubble, the solar wind began stripping away its atmosphere like peeling layers off an onion. The pressure dropped, the air thinned, and the once blue sky turned pink with dust. Meanwhile, Earth was holding its cards close. It had a strong magnetic field, a stable orbit, and just enough gravity to keep its atmosphere and water from drifting off into space. Every small advantage compounded over time. The result? One planet got rainforests, oceans, and memes. The other got craters, wind, and regret. It's easy to think of this as luck, but really it's a delicate balance of cosmic physics. A few degrees colder, a slightly weaker magnetic field, a few unlucky impacts. And Earth could have been the red planet instead. What makes this story even more fascinating is that the two worlds didn't diverge overnight. For hundreds of millions of years, they evolved in parallel. While Earth was just starting to form its first continents, Mars was already experimenting with rivers and lakes. It's entirely possible that both worlds were habitable at the same time. A brief, shining window where life could have sparked on both. Maybe, just maybe, Mars once had its own version of biology before it all slipped away. If so, Earth isn't unique. It's just the one that managed to hang on. It's humbling to think how fragile that difference is. We live on a planet that works because 1,000 small factors line up perfectly every day. The right distance from the sun, the right rotation speed, the right amount of gravity, and a magnetic field that never takes a day off. If even one of those fails, we might start looking a lot more Martian than we'd like. You could say the universe doesn't play favorites. It just flips coins made of stardust, and this time, Earth called heads. So next time you see Mars in the night sky, glowing like a distant ember, think of it as the alternate ending to our story. A version where oceans never formed, where clouds never rained, where life never got its shot. It's a reminder that our world's beauty wasn't inevitable. It was a near miss, a cosmic coin toss that landed just barely in our favor. And that, in itself, is reason enough to treat this lucky blue dot with a little more care. After all, no one wants to find out what it's like to be the sequel to Mars. In the chaotic nursery of the early solar system, planets were forged through violent collisions and cosmic tantrums. Earth and Mars started out almost as equals. Two rocky worlds, with molten hearts and a chance at atmospheres. The difference? Earth had better luck dodging space boulders, while Mars took a few too many hits to the face. If you could travel back 4.5 billion years, you wouldn't recognize the solar system. There were no neatly arranged planets gliding in peaceful orbits. It was a demolition derby of cosmic proportions. Dust, gas, and rock fragments filled the space around the young sun, colliding, sticking, and sometimes exploding apart. This whirling chaos was called the protoplanetary disk, a sort of cosmic soup where gravity was the chef, stirring and clumping ingredients until something resembling planets began to form. Every future world started as grains smaller than sand. But in the vacuum of space, small things have a way of finding each other. Electrostatic forces pulled particles together, creating pebbles, then boulders, then mountain-sized objects called planetesimals. These planetesimals were the universe's first real builders, and also its first wrecking balls. When they collided, it wasn't gentle. These were impacts that could vaporize continents before continents even existed. Yet, through this chaos, mass begot gravity, and gravity begot planets. Earth and Mars were born out of this same violent ballet. Just different dancers in slightly different parts of the floor. Both formed within what astronomers call the terrestrial zone, close enough to the sun for rock and metal to survive, but too hot for ice. Here, materials like iron, nickel, and silicates fused into dense worlds with molten cores. The early versions of both planets glowed with internal heat, their surfaces seas of lava, their skies thick with toxic gases. It was a hellish start. Imagine a landscape made of liquid rock, thunder made of stone, and rain that could dissolve metal. But even in this inferno, small differences began to emerge. Earth formed slightly closer to the sun, where there was more material in the disk to feed its growth. Mars, a bit farther out, ran out of building blocks early. You could say Mars was the kid at the buffet who arrived late. By the time it got there, all the good stuff was gone. This difference in available material gave Earth about twice the mass of Mars, which would prove crucial. Bigger planets stay hotter longer, develop stronger gravity, and have more geological stamina. Smaller planets cool down, slow down, and eventually give up the ghost. Still, for a while, both planets were neck and neck. Each was undergoing a process known as planetary differentiation, where heavy elements like iron and nickel sank inward to form a core, while lighter silicates floated upward to create a crust. This layering was key. It meant both worlds could sustain volcanic activity, magnetic fields, and atmospheres. Picture the early solar system as a giant foundry, forging planets out of chaos and fire. The young sun blazed brighter than it does today, solar flares erupting with the force of billions of hydrogen bombs. Asteroids rained down constantly, heating the newborn worlds even further. It wasn't a peaceful upbringing. In fact, one of Earth's most defining moments came from violence, a collision so enormous it reshaped our destiny forever. A Mars-sized object, often called Theia, slammed into Earth with unimaginable force. The impact was so catastrophic it vaporized parts of both planets, splashing molten rock into orbit that eventually coalesced into our moon. It was the cosmic equivalent of losing a tooth and getting a satellite as a consolation prize. Mars, for its part, experienced its own bombardments, but never quite the same cataclysmic merger. It was pelted relentlessly, leaving its surface pockmarked with scars that still tell the tale today. Some of its craters are so old they predate most of Earth's rocks. Because Mars lacked Earth's geological vigor, no plate tectonics to recycle the crust, its surface became a fossil record of every punch it ever took. It's like looking at a boxer who never healed between fights. In those fiery early ages, impacts weren't just destructive, they were also creative. Asteroids brought essential ingredients like carbon, nitrogen, and even water locked inside minerals. These elements would later form the building blocks of life. Earth, with its greater gravity, captured more of this precious cargo. Mars got some too, but not nearly enough to sustain the same richness. The early bombardment phase, often called the late heavy bombardment, might sound like something out of a metal band's album, but it was nature's way of seasoning planets with the ingredients for chemistry. As the chaos settled and the debris thinned out, both worlds began to cool and stabilize. Earth's molten surface hardened into a thin crust, cracking and reshaping under immense internal pressure. Volcanoes exhaled gases, creating a primitive atmosphere dense with carbon dioxide and water vapor. Mars followed a similar path, but with less vigor. Its smaller size meant less internal heat, fewer volcanic outbursts, and a weaker gravitational grip on its atmosphere. It was a smaller engine running out of fuel too soon. By the time the sun's tantrums mellowed and the solar wind quieted, Earth and Mars stood as two survivors of cosmic adolescence, battered, burned, but still standing. They were shaped by the same forces but destined for different fates. One would become a thriving cradle of life, while the other would fade into a cold, rusty memory of what might have been. Looking back, the fiery birth of planets was less a gentle origin story and more a cosmic boot camp. It tested who could hold their atmosphere, who could stay warm, who could take the hits and keep spinning. Earth emerged with a few extra bruises and a companion moon. Mars emerged smaller, lonelier, and forever marked by its youth. In the end, the early solar system didn't play favorites. It simply rewarded endurance. And, as it turns out, in the business of becoming a living world, survival is the best talent you can have. Earth's magnetic field is basically an invisible superhero cape, deflecting deadly solar wind. Mars once had one too, but it fizzled out like a bad Wi-Fi signal. Without that shield, Mars's atmosphere got stripped away, leaving it bald and breathless, while Earth kept her protective bubble intact. To understand why this invisible force matters so much, picture the sun not as a calm golden orb, but as a raging furnace that hurls tantrums across space. Every second, it spits out a storm of charged particles, protons and electrons moving at insane speeds. This solar wind doesn't politely knock, it slams into anything in its path. Planets that lack protection get their atmospheres slowly sandblasted into oblivion. The only reason we can step outside on Earth without being microwaved or losing our breath to space is because our planet has an electromagnetic force field, literally. That field comes from deep within Earth's belly, in a layer called the outer core. Down there, roughly 3,000 kilometers beneath your feet, molten iron and nickel swirl like a churning ocean of fire. As this metal moves, it generates electric currents, and those currents create magnetic fields. The process is called the geodynamo, and it's basically nature's most hardcore generator, one that's been running non-stop for billions of years. Without it, Earth would look a lot less blue and a lot more Martian. But here's the twist. Mars once had its own dynamo. For a few 100 million years after it formed, Mars's core was hot and lively, spinning with molten metal that produced a magnetic shield of its own. For a time, that field deflected the sun's radiation just as Earth's does today. It might have even helped Mars keep an atmosphere thick enough for clouds, rain, and maybe oceans. In its youth, Mars wasn't the dry, dusty world we know. It was a planet with promise. So, what went wrong? In short, Mars's heart went cold. Because it was smaller than Earth, it lost its internal heat faster, like a mug of coffee forgotten on a cold morning. Once the core solidified, the dynamo died. And when the dynamo died, the magnetic field went with it. Mars lost its superhero cape, and suddenly the solar wind had a direct line of attack. Imagine peeling an orange in slow motion. That's what happened to Mars's atmosphere. Over millions of years, charged particles from the sun struck the upper layers of its air and knocked molecules into space. Bit by bit, the carbon dioxide, nitrogen, and water vapor that once insulated the planet were stripped away. The pressure dropped so low that liquid water couldn't survive on the surface anymore. It either froze solid or evaporated into the thinning air. Mars didn't so much lose its atmosphere as it was quietly robbed of it. Meanwhile, Earth's magnetic field held strong. It's not static. Our planet's field wobbles, flips, and pulses like a living thing. Every few 100,000 years it even reverses with the north and south magnetic poles swapping places. During those flips, the field weakens temporarily, but never disappears entirely. This resilience is one of Earth's greatest superpowers. Even when the field flickers, the molten metal below keeps the dynamo alive, ensuring our protection continues. Without this shield, life on the surface would face a constant onslaught of radiation. The solar wind would erode our atmosphere, strip away the ozone layer, and make the sky glow with perpetual auroras of doom. You might see more northern lights, sure, but you'd also see your DNA unraveling faster than a cheap sweater. The magnetic field also does something else remarkable. It connects us to the sun in a delicate electromagnetic dance. When solar storms hit Earth, the field bends and ripples, directing charged particles toward the poles. That's what causes the auroras, the shimmering curtains of green and pink light that ripple through polar skies. They're not just pretty, they're the visible fingerprints of our planet's defense system at work. Every time you see one, you're watching Earth's shield deflecting a cosmic punch. Mars still has tiny patches of magnetism trapped in its crust, fossilized remnants of its long-dead dynamo. NASA's spacecraft have mapped these magnetic ghosts, scattered across the southern hemisphere like faint echoes of a forgotten melody. They're evidence that Mars once had a global field strong enough to protect it, before everything went quiet. It's like finding the ruins of a lost civilization written into the rock. Scientists have even tried to imagine ways to bring Mars's magnetic field back. Some propose building an enormous electromagnetic shield at a point in space between Mars and the Sun to deflect a solar wind the way Earth's field does naturally. Sounds like science fiction, and to be honest, it still is, but it shows how central magnetic fields are to the idea of making planets livable. Without one, terraforming Mars would be like trying to heat a house with all the windows open. The contrast between Earth and Mars isn't just about luck, it's about longevity. Earth's molten core has stayed active for billions of years because our planet is big enough to trap heat from its formation and from radioactive decay deep inside. That steady churning keeps the dynamo humming. Mars, smaller and quicker to cool, couldn't keep its heart beating. The magnetic miracle on Earth is really the story of a planet that never stopped moving inside. So the next time you see a compass needle twitching, think about the invisible machinery beneath your feet making that possible. It's not just pointing north, it's pointing to one of the reasons you exist. Our world's magnetic field is a shield, a sculptor, and a storyteller. It has written the history of survival into our skies, and in doing so, separated the living from the lifeless. Mars may have lost its cape, but Earth still wears hers proudly, shimmering in the unseen glow of a planet that refuses to go quietly into the cosmic storm. Both planets once had rivers, lakes, maybe even oceans. Mars dried out because its weak gravity couldn't hold on to water vapor, while Earth held tight like a clingy X. The result? We have beach vacations. Mars has dust storms the size of continents. To understand the story of water on these two worlds, you have to think of the early solar system as a cosmic plumbing experiment gone wrong. Picture two planets forming side by side, both steamy and hot, both wrapped in thick atmospheres full of water vapor, carbon dioxide, and other volatile gases. At first, neither had liquid water. Everything was vaporized by the leftover heat of formation and the relentless bombardment from space debris. But as the chaos calmed and both planets began to cool, something miraculous happened. Water began to rain. On Earth, this rain didn't just drizzle, it poured for thousands of years. The planet's surface hissed as oceans formed, steam condensed, and the first seas gathered in the planet's lowlands. Those early oceans were muddy, acidic, and toxic. But they were liquid, and that made all the difference. Earth's gravity was strong enough to hold on to the water vapor and keep it from drifting off into space. It was the start of a stable hydrological cycle: evaporation, condensation, rainfall, a planetary heartbeat that would shape everything that came after. Mars, at the same time, might have looked surprisingly Earth-like. The evidence is written in its surface. Winding river valleys that once carried flowing water, deltas where rivers emptied into lakes, and vast plains that may have been ancient ocean floors. If you could travel back 3 or 4 billion years, you might have seen clouds drifting over Martian mountains, rainfall darkening the rusty soil, and streams carving their way toward shimmering lakes. Mars wasn't always a desert. It had a wet, active climate. For a brief time, both planets shared a watery destiny, but that partnership didn't last. Mars, being smaller, had weaker gravity, and with its magnetic field gone, the solar wind had a direct line of fire to its atmosphere. When ultraviolet light from the sun hit the upper atmosphere, it split water molecules into hydrogen and oxygen. The hydrogen, being light, escaped into space, never to return. The oxygen reacted with iron in the Martian crust, giving the surface its distinctive red rust color. In short, Mars's oceans didn't just evaporate. They oxidized the entire planet. Mars is, quite literally, rusted dry. Meanwhile, Earth clung to its water like it was the last cup of coffee in the universe. Our stronger gravity kept light gases from escaping, and our active volcanoes kept recycling water vapor back into the atmosphere. Even when asteroid impacts and ice ages tried to steal it, water always found a way back into circulation. It seeped underground, froze in glaciers, and re-emerged in rainstorms. Earth's relationship with water is less of a fling and more of a codependent marriage. It's complicated, but it works. The consequences of this difference are monumental. On Earth, water became the great sculptor of landscapes and the midwife of life. It carved canyons, smoothed mountains, and turned rock into fertile soil. More importantly, it provided the solvent for the chemistry of life. Every living cell on Earth is basically a tiny water balloon performing molecular magic. Water dissolves nutrients, carries heat, and stabilizes temperature. Without it, life as we know it would be as impossible as surfing on Mars. Mars, deprived of liquid water, froze into silence. The last trickles of water likely retreated underground, where some may still remain locked as ice or brine. NASA's rovers have found evidence of recurring slope lines, dark streaks that appear in Martian summer and fade in winter, possibly caused by salty water briefly melting beneath the surface. But these are not rivers as we know them. They're ghosts of a hydrological past, whispers of what Mars once had and lost. Even today, the two planets show how differently water defines a world. On Earth, the ocean dominates, covering 70% of the surface and driving weather, climate, and biology. It regulates temperature by absorbing heat and releasing it slowly, a planetary thermostat that keeps us from boiling or freezing. Mars, without that buffer, experiences temperature swings that would make any thermostat cry. Daytime can be warm enough to melt ice, but nighttime plunges far below freezing. Without oceans to distribute heat, the planet is trapped in extremes, scorching sunlight by day, Arctic chill by night. There's also a strange irony to how water shaped their appearances. Mars's red deserts look dry, but they were born from water's betrayal. The same oxidation that colored the soil red happened because of water interacting with rock and atmosphere billions of years ago. Earth, meanwhile, hides its geological scars beneath oceans and weathering. Mars wears its heartbreak openly. Earth lets the tide erase it every night. Scientists still debate where Earth's water came from. Some believe it was part of the planet's original material, locked in minerals that released it through volcanic outgassing. Others think it was delivered by icy comets and water-rich asteroids after formation. Mars likely got its water the same way, but being smaller, it simply couldn't hold on to it for the long haul. Imagine 2 cups of boiling soup, one large, one small. The small one cools and evaporates faster. Mars's cup ran dry early, while Earth's kept simmering. Today, the search for life on Mars revolves entirely around this lost water. If microbes ever existed there, they lived in that brief window when the planet was wet and warm enough to sustain them. Perhaps they still cling to existence underground, shielded from radiation in salty pockets of liquid. Every rover that scrapes Martian soil is essentially asking the same question. Did water ever get the chance to make life spark before it vanished? The water wars between Earth and Mars weren't fought with battles, but with balance. Gravity, temperature, and time decided the victors. Earth held tight and stayed blue. Mars let go and turned red. Our oceans are living archives of planetary success. Mars's dry riverbeds are memorials to a world that almost made it. And maybe that's the most haunting part. Mars didn't fail for lack of trying. It just lost the fight against the sun. If there's a lesson in that, it's this. Water is not just something planets have. It's something they must constantly defend. Without it, there are no clouds, no rivers, no whispers of life. Earth fought to keep its water, and in doing so, it kept everything that makes it home. Mars lost that battle long ago, and now every dry canyon and frozen crater stands as a quiet reminder of what happens when a planet's heart forgets how to hold on. Volcanoes on Earth gave us air, land, and life. On Mars, they just gave up. Olympus Mons is the biggest volcano in the solar system, but it's been asleep for eons. Meanwhile, Earth's volcanoes kept puffing like coffee machines, recycling gases that kept our climate alive. If you want to understand why volcanoes matter, you have to think of a planet not as a solid rock, but as a living engine. Deep inside, heat churns, pressure builds, and molten rock, magma, rises toward the surface, looking for a way out. When that magma erupts, it doesn't just spew lava, it breathes. Volcanoes are the lungs of a planet, exhaling gases that shape the sky above and the world below. On Earth, every puff of volcanic smoke has been part of a long, ongoing dialogue between the planet's interior and its atmosphere. Billions of years ago, when the Earth was still cooling from its violent birth, the first volcanoes were more like cracks in the crust, venting enormous amounts of gas and molten rock. They filled the sky with carbon dioxide, nitrogen, and water vapor, an early cocktail of gases that would later become the atmosphere. Before volcanoes, Earth was silent and airless. After them, it was noisy and breathable. Volcanoes didn't just build the air, they built the land itself. The continents we walk on were born from ancient eruptions that poured layer upon layer of basalt and ash, hardening into rock. Even island chains like Hawaii are volcanoes still in progress, Earth's crust slowly bubbling new land out of the deep. Without volcanoes, our world would be smaller, flatter, and far less interesting. But on Mars, things played out differently. The planet started off with volcanic ambition. It has some of the most spectacular volcanoes in the solar system. The crown jewel is Olympus Mons, a mountain so tall it pierces the thin Martian atmosphere. It stands nearly 3 times higher than Mount Everest and sprawls across an area the size of France. If you stood at its base, you wouldn't even see the summit. It would curve out of sight with the planet's horizon. Olympus Mons and its volcanic neighbors. Arsia Mons, Pavonis Mons, and Ascraeus Mons are monuments to a planet that once burned bright. For hundreds of millions of years, Mars was geologically alive, with magma bubbling beneath its crust and eruptions shaping its surface, and ancient lava plains cover vast stretches of the planet, frozen mid-flow like waves turned to stone. If you could see Mars in its prime, you'd have witnessed rivers of molten rock glowing under a pink sky. So why did Mars stop? The short answer, it ran out of energy. Volcanoes are powered by a planet's internal heat. And that heat comes from 2 main sources: leftover energy from formation and radioactive decay within the core. Earth, being larger, retained enough heat to keep its interior molten. Mars, smaller and faster to cool, saw its inner fires dim. As the core solidified, volcanic activity dwindled, and eventually it went silent. Olympus Mons hasn't erupted in tens of millions of years. On a planetary timescale, that's like someone taking a nap that never ends. Earth's volcanoes, meanwhile, never stopped playing their part in the grand atmospheric cycle. They release carbon dioxide, sulfur, and water vapor, gases that trap heat and maintain temperature balance. Without them, the atmosphere would slowly thin out as gases escaped into space or were locked away in rocks. Volcanoes are the climate regulators we didn't know we needed. Every time they erupt, they're not just causing chaos, they're resetting the thermostat. It's a delicate system. Too many eruptions, and the air fills with ash, blocking sunlight and plunging the planet into a temporary chill. Too few, and carbon dioxide levels drop too low, risking a global freeze. Somehow, Earth has managed to maintain a rhythm that keeps things in balance. Not perfect, but just enough for life to persist. Mars, lacking that ongoing volcanic pulse, lost not only its internal heat, but its ability to recycle atmospheric gases. Once the volcanoes died, the planet began to suffocate. There's a strange poetry in how volcanoes create the conditions for life, but can also end it. On Earth, eruptions have sparked both disaster and renewal. Massive events like the eruption of Mount Toba 74,000 years ago nearly wiped out humanity's ancestors. But those same eruptions replenished the soil with minerals, seeded oceans with nutrients, and helped stabilize the air. Volcanic ash, for all its destruction, is one of the most fertile materials on Earth. It's the paradox of creation through chaos, destruction making way for life. Mars, without its volcanic lifelines, became a planet without renewal. Once its volcanoes shut down, its carbon dioxide stopped being replenished, its atmosphere thinned, and temperatures dropped. Over time, the planet became cold and still. Olympus Mons stands as a frozen memorial, a colossal reminder that geological silence can be as deadly as any catastrophe. Interestingly, scientists think Mars's colossal volcanoes might have grown so large precisely because the planet lacked plate tectonics. On Earth, the crust constantly moves. When magma rises through a volcanic hotspot, the crust shifts above it, spreading the lava over different areas. That's why Hawaii is a chain of islands rather than one massive peak. Mars's crust, on the other hand, stayed still. Magma erupted through the same spot for millions of years, piling up higher and higher until it created the gargantuan mountains we see today. In other words, Olympus Mons isn't just big. It's the planetary equivalent of overdoing it because no one said stop. If Earth's volcanoes are a conversation between surface and core, Mars's were more like a single shout that echoed and faded into silence. And that silence changed everything. Without active volcanoes, Mars couldn't recycle its gases, couldn't sustain a thick atmosphere, and couldn't keep its surface warm. Its story became one of gradual stillness, a once vibrant world turning into a geological ghost. Back on Earth, volcanoes continue to rumble and hiss, sometimes violently reminding us of their power. But as destructive as they seem, they are also the reason we breathe, eat, and live. Every gust of air once passed through volcanic vents. Every grain of fertile soil has ash in its ancestry. We owe them more than we realize, and so when you see a volcano spewing smoke into the sky, remember, it's not just venting, it's keeping the planet alive. Earth's volcanoes are the planet's heartbeat, always pumping, always renewing. Mars, once alive with fire, now lies quiet. Its heartbeat stopped. its world frozen mid-breath. The difference between a living planet and a dead one, it turns out, might just be a volcano refusing to give up. For billions of years, Earth's air was a toxic soup of gases you'd never want to breathe. Then came cyanobacteria, the original green influencers, who started pumping out oxygen. Mars never got that makeover. Its surface stayed barren, while Earth literally learned how to breathe. Let's rewind to a time when fresh air was a death sentence. Picture early Earth, volcanoes belching out carbon dioxide, methane, sulfur dioxide, and ammonia. Skies stained orange, lightning cracking through clouds of poison. The oceans were thick with dissolved iron, the land bare and lifeless. If you could somehow stand on the shore, ignoring that you'd immediately choke, you'd see a planet that was more alien than Mars looks today. The air was suffocating, the seas were acidic, and sunlight filtered through a haze of toxic gas. Yet in this hostile world, something miraculous was brewing in the shallows. Life had already begun. Tiny, single-celled organisms that didn't need oxygen because there wasn't any. They were anaerobes, ancient microbes that thrived in the chemical chaos of early Earth. These creatures lived by munching on whatever molecules were available, breaking down compounds in the water for energy. Then, somewhere around 2.5 billion years ago, evolution pulled off one of its greatest tricks. A microbe learned how to harness sunlight. These new pioneers were cyanobacteria, and they discovered photosynthesis, the art of turning sunlight, water, and carbon dioxide into food. The byproduct of that reaction was oxygen, which at the time was about as useful to life as smoke in a submarine. But the cyanobacteria didn't care. They just kept releasing it. Slowly, molecule by molecule, they began to change the world. At first, that oxygen had no place to go. The oceans were full of iron, which reacted with the oxygen to form rust. Literally, the rusty iron settled onto the ocean floor, layer after layer, creating massive deposits of banded iron formations that we still mine today. For millions of years, the oxygen never made it out of the oceans. It was too busy turning the seafloor into a scrapyard. Then came the tipping point. Around 2.4 billion years ago, the oxygen finally broke free into the atmosphere. It was one of the most dramatic planetary makeovers in history, the Great Oxygenation Event. Suddenly, Earth's sky began to shift from orange to blue, and the air went from deadly to breathable. Well, eventually. For the first time, oxygen levels rose high enough to support complex chemistry, paving the way for future life forms that would use it to burn food for energy. This was the moment Earth learned to exhale. But for many of its original inhabitants, it was the apocalypse. The oxygen that made the planet habitable for us was toxic to the microbes that came before us. It ripped apart their cell walls and interfered with their metabolism. Entire microbial ecosystems were wiped out or forced into oxygen-free hiding spots, like the deep sea or underground. Life on Earth, quite literally, killed its ancestors to make room for its descendants. Evolution can be dramatic like that. Mars, meanwhile, never had a great oxygenation event. It likely had water and energy sources early on, but not the thriving biological machinery to transform its atmosphere. Without liquid oceans for life to flourish in, there was no vast stage for photosynthetic microbes to perform their planetary renovation. Its carbon dioxide-heavy air stayed that way. Mars never had a microbial revolution. It stayed stuck in pre-oxygen times, its chemistry frozen in the ancient past. The great oxygen upgrade didn't just change the air, it changed the ground, the oceans, and even the color of the planet. As oxygen accumulated, new minerals formed that couldn't exist before, like hematite and magnetite, both iron oxides. These minerals locked oxygen into the crust, storing it like a planetary memory card. The oceans turned from murky greenish-brown to clearer blue as the iron settled out. Even the sky brightened, scattering light in a way that would look familiar to us now. For the first time, the world began to look like the one we live on. It took hundreds of millions of years for oxygen levels to climb high enough for complex life to appear. But once they did, evolution exploded. Oxygen allowed for respiration, a much more efficient way to generate energy than the old anaerobic methods. Suddenly, cells could grow larger, specialize, and combine into multicellular organisms. Every breath you take today is powered by that ancient invention, a chain reaction started by microscopic architects in shallow seas billions of years ago. It's almost poetic that life created the very gas it needed to evolve. Without oxygen, there'd be no animals, no plants, no ozone layer to block harmful ultraviolet radiation, and no humans to argue about climate change on the internet. Oxygen made Earth not just habitable, but self-regulating. When oxygen levels dropped, photosynthesis sped up. When they rose too high, fires and decay pulled it back down. It became the invisible balancing act that has kept our planet stable for ages. Mars, by contrast, became a world without breath. Its lack of a biosphere meant no photosynthesis, no oxygen production, and no protective ozone. Ultraviolet light from the sun sterilized its surface, breaking apart any organic molecules that dared to form. Even if early microbes once existed there, they never got the chance to reinvent the atmosphere. Mars stayed chemically stagnant, locked in a time capsule from the dawn of the solar system. When we look at Mars today, a world of iron oxides and silence, we're looking at the planet Earth might have been, if not for that cyanobacterial breakthrough. The difference between red and blue is, quite literally, oxygen. The rust-red deserts of Mars are the color of what happens when oxidation occurs without renewal. Iron reacting with oxygen billions of years ago and never being replenished. Earth's blue sky, on the other hand, is the signature of an atmosphere in motion, one that still breathes, still changes, still lives. The great oxygen upgrade wasn't just a turning point for Earth, it was the universe's proof of concept that life could shape an entire planet. It was biology rewriting geology, microbes teaching the air how to sustain breathers. And it reminds us of something humbling. We owe every lungful of oxygen to creatures too small to see. The next time you take a deep breath, thank a cyanobacterium. It may have been the tiniest life form, but it pulled off the biggest makeover in the solar system, turning a suffocating rock into a living, breathing world. Earth's climate is like a drama series with plot twists, but somehow we've stayed in the habitable zone season after season. Mars, on the other hand, jumped straight from tropical pilot episode to frozen finale. One lost magnetic field later, and the red planet became a desert that forgot its own script. Every planet's climate begins as a conversation between the sun and its atmosphere, a delicate negotiation of energy, distance, and chemistry. Too much sunlight and you cook, too little and you freeze. The so-called habitable zone is where temperatures allow water to exist as a liquid, but simply being in that zone doesn't guarantee a happy ending. Earth and Mars both started in this cosmic sweet spot, yet their fates diverged spectacularly. Earth became a masterpiece of moderation. Mars became a cautionary tale in climate collapse. Let's start with Earth, the gold standard drama queen of climate stability. From space, it looks tranquil, clouds swirling, oceans glimmering, continents glowing in soft hues. But zoom in, and you'll find a planet that has survived some of the most extreme mood swings imaginable. There have been global ice ages where the oceans froze nearly to the equator, and greenhouse episodes so warm that crocodiles lounged in what's now the Arctic. And yet, through it all, life persisted. Somehow, Earth has a built-in knack for pulling itself back from the brink. It's like a show that keeps getting renewed, no matter how wild the finale gets. This resilience comes from feedback loops, natural systems that act like planetary thermostats. When things get too hot, weathering of rocks increases, pulling carbon dioxide out of the atmosphere and cooling the planet. When things get too cold, volcanic outgassing pumps more carbon dioxide back into the air, trapping heat and thawing things out again. It's the slowest seesaw in existence, but over millions of years it keeps the balance. It's called the carbon silicate cycle, and it's basically Earth's version of a climate maintenance subscription. Quiet, reliable, and always auto-renewing. Mars, on the other hand, unsubscribed early. In its youth, it likely enjoyed a mild climate. Ancient riverbeds and dried deltas tell us there were warm periods long enough for liquid water to flow. The sun, in its early years, was fainter than today, so Mars must have had a thick atmosphere rich in greenhouse gases to trap enough heat. For a while, the red planet may have been blue, but then came the plot twist. Without a strong magnetic field to fend off the solar wind, Mars's atmosphere began to erode. As the gases thinned, so did the greenhouse effect. Temperatures dropped, water froze, and the once dynamic climate seized up. What was once a global hydrological system became a frozen desert. Today, daytime temperatures near the equator might flirt with a mild 20 degrees Celsius, but at night, they plunge below -100. The air is so thin that liquid waters can't exist on the surface for more than a few moments. It boils away or freezes instantly. Mars went from potentially balmy to brutally bipolar. Meanwhile, Earth's atmosphere thickened and diversified. Volcanic emissions, plant respiration, ocean circulation, all these forces became part of a living, breathing climate engine. The presence of oceans gave Earth a thermal buffer, absorbing heat during the day and releasing it at night. Mars never had that luxury. Its smaller size meant less gravity to hold an atmosphere and no tectonic system to recycle gases. Its climate didn't just cool, it flatlined. But even with all its built-in balancing acts, Earth's climate has had cliffhanger moments. Around 700 million years ago, it nearly froze solid during a period scientists call Snowball Earth. Ice spread across the continents and oceans, reflecting sunlight and reinforcing the chill. For millions of years, the planet was trapped in a feedback loop of ice and darkness. If volcanoes hadn't continued to belch carbon dioxide into the air, building up enough greenhouse gases to warm things again, Earth might have joined Mars in eternal winter. Instead, the ice eventually melted, and the rebound ushered in a burst of evolutionary creativity that led to multicellular life. Talk about a dramatic comeback. The lesson here is that climate stability is not the same as climate stillness. Earth's climate has never been static. It's a dynamic, restless system constantly juggling inputs from the sun, oceans, volcanoes, and life itself. The miracle is not that it changes, but that it stays within boundaries that keep liquid water and life possible. Mars, stripped of atmosphere and ocean, lost the ability to self-correct. Once it tipped toward cold, it had no way back. There's a quiet tragedy in that. Imagine a world where rain once fell, where rivers carved canyons, where fog clung to crater rims. Then, as the atmosphere slipped away, the last drops evaporated, clouds disappeared, and the planet fell silent. It's as if Mars skipped all the middle seasons and jumped straight to the end credits. Its climate story froze in place, literally. Earth, on the other hand, learned to adapt. Its oceans act like enormous heat batteries, storing energy and releasing it gradually. Its biosphere, everything from forests to plankton, plays an active role in regulating temperature. Plants absorb carbon dioxide. Clouds reflect sunlight. Ice sheets adjust the planet's brightness. Even the tiniest life forms help shape the weather. In that sense, Earth isn't just a planet. It's a co-authored climate novel, written by geology, biology, and physics together. Mars reminds us what happens when that collaboration ends. No oceans to buffer temperature swings. No thick air to trap warmth. No biosphere to breathe or balance gases. The red planet is a frozen warning sign, orbiting quietly beside us. A reminder that planetary climate is a privilege, not a guarantee. And now, as Earth's own carbon dioxide levels rise faster than ever, we're writing a new episode in the series, one where the protagonist starts meddling with the thermostat. The difference is that this time, the cliffhanger isn't caused by cosmic forces or magnetic failure. It's us, and the preview isn't pretty. But if history has taught us anything, it's that Earth is resilient. It's endured impacts, ice ages, and near extinctions and still found balance. Mars couldn't adapt because it lost its tools. Earth still has them: oceans, atmosphere, life. The only question is whether we'll let those tools keep working or force our planet to audition for the role of Mars in a sequel nobody wants to watch. In the end, climate is the memory of a planet's soul, how it breathes, reacts, and evolves. Mars's memory froze long ago, a story cut short. Earth's story is still being written, its balance fragile, but alive. And for now, we're lucky enough to still be part of the cast. Both planets got pelted by asteroids in the early days, but Earth had one advantage: a bigger size and stronger gravity, which helped it hold on to its atmosphere. Mars, smaller and more fragile, lost chunks of itself to space. You could say Mars got ghosted by its own air. Long before either world had continents, oceans, or breathable skies, the solar system was a demolition zone. The early planets were still forming, and the space between them was filled with leftover debris. Millions of chunks of rock, ice, and metal left over from the birth of the sun. Gravity was the universe's favorite party trick, pulling these fragments together and sometimes violently crashing them apart. This period, called the Late Heavy Bombardment, was less of a meteor shower and more of a cosmic shooting gallery where every planet took a hit. For about 500 million years, asteroids and comets hammered the inner planets with relentless fury. Each collision unleashed energy equivalent to millions of nuclear bombs, reshaping entire surfaces and sometimes vaporizing whole atmospheres. It wasn't a great time to own real estate anywhere near the sun. Yet somehow, Earth survived this chaos and went on to become a cradle for life, while Mars was left scarred and stripped. The difference lay in the way each world handled getting punched in the face by space rocks. Earth's larger size and thicker gravitational grip acted like a safety net. When asteroids slammed into its surface, the planet absorbed the damage, melted, reformed, and tried again. Its gravity also helped it hold on to its atmosphere despite the battering. Each impact certainly caused devastation. Oceans boiled, continents cracked. But Earth's robust gravity kept the gases from drifting away completely. It was like getting knocked down in a fight but still holding on to your breath. Mars, on the other hand, had a much harder time staying on its feet. Being only about half the size of Earth, its weaker gravity meant it couldn't hold on to its atmosphere as tightly. When large asteroids struck, the blasts could send atmospheric gases hurtling into space. Every impact peeled away another layer of protection. Over time, that added up. Mars's atmosphere became thinner, its air colder, and its chances for habitability dwindled. The evidence of this ancient bombardment is still written on both worlds, but especially on Mars. Earth has erased most of its scars through erosion, tectonic recycling, and weathering. Volcanoes rebuild, rain reshapes, and time heals. Mars has none of those luxuries. Its surface is a museum of craters, frozen in time. The largest of them, Hellas Basin, spans over 2,000 kilometers across and is 9 kilometers deep, the result of an impact that would have shaken the entire planet. When that asteroid hit, it didn't just leave a crater, it likely sent shock waves through Mars's core and atmosphere, further weakening an already fragile world. For Earth, the bombardment wasn't all bad news. Those incoming asteroids and comets carried valuable cargo, water, carbon compounds, and other building blocks of life. Many scientists believe that much of Earth's ocean water may have arrived this way, delivered by icy comets that melted upon impact. Each collision was violent, yes, but also generous. Like a cosmic delivery service that forgot to knock before dropping off the goods. Without those deliveries, Earth might have remained a dry, lifeless rock. Mars, too, received its share of watery gifts, but again, its smaller mass and lack of atmospheric staying power made it harder to keep them. The late heavy bombardment eventually eased, but the solar system never truly stopped throwing rocks. Even after things quieted down, stray asteroids occasionally found their way toward the inner planets. One such visitor, about 66 million years ago, famously ended the reign of the dinosaurs on Earth. That impact, near modern-day Mexico, created a crater almost 200 kilometers wide and plunged the world into temporary darkness. Yet, from that catastrophe, life bounced back stronger, paving the way for mammals, and eventually, us. Mars wasn't so lucky with its late arrivals. The lack of a dense atmosphere meant that smaller meteoroids could strike its surface directly instead of burning up like they do on Earth. Today, new craters appear on Mars every year, some large enough to spot from orbit. The planet still wears its pockmarked history proudly, while Earth constantly scrubs and repaints its surface. Mars is the cosmic equivalent of someone who never fixed their childhood scrapes. Earth is the one that learned skincare routines. One fascinating twist is that some of the rocks blasted off Mars during ancient impacts have actually landed on Earth. We've found them, meteorites containing Martian minerals and trapped gas bubbles identical to Mars's atmosphere. In a strange reversal, pieces of Mars have traveled across space and crash-landed here. It's planetary recycling on a cosmic scale. And it raises an intriguing question. Could the exchange have gone both ways? Could early Earth have sent life-bearing rocks to Mars? If so, maybe some tiny stowaway microbes got their one-way ticket to the red planet billions of years ago. The universe, it seems, has a knack for messy crossovers. When we think of bombardments, we imagine destruction. But in the long view of planetary evolution, they're also agents of change. Impacts release heat, stir chemical reactions, and reshape landscapes. They can sterilize, but they can also create new opportunities. On Earth, those chaotic centuries helped carve the conditions for oceans, continents, and eventually life. On Mars, they may have done the opposite, stripped away too much too early, leaving a planet with all the potential but none of the staying power. Even today, both worlds continue to dodge cosmic debris. Our moon, pocked with craters, stands as a visible reminder of what happens without an atmosphere to shield you. Earth's atmosphere, dense and dynamic, burns up most small meteors before they hit the ground. Mars, thin-skinned and unprotected, takes the full impact. You could say it's still paying for its size disadvantage. Every shooting star on Mars is just another car in slow motion. The bombardment age may have ended billions of years ago, but its fingerprints are everywhere. Every breath we take owes something to the violent past that shaped our world. And every crater on Mars tells the story of a world that couldn't quite heal. Two planets born in the same storm, battered by the same cosmic fists. One learned how to recover, the other never did. In the end, the difference wasn't in how often they were hit, but how they endured. Earth's strength was its gravity, its ability to hold on, to air, to water, to the ingredients of life. Mars couldn't hold on at all. The cosmos threw the same punches, but only one planet learned how to stand back up. Earth's stable tilt gives us mild seasons and climate predictability. Mars's axis, on the other hand, wobbles like a toddler on a sugar rush, making its climate go from ice age to heat wave without warning. Stability might be boring, but in space weather, boring means life. If the solar system were a family portrait, you'd notice that most of the planets don't sit up straight. Each one leans at a different angle, spinning like a slightly tipsy top around the sun. This tilt, known as axial obliquity, decides everything about a planet's seasons, weather, and long-term climate. Too much tilt, and your world turns into a meteorological roller coaster. Too little, and it becomes monotonously frozen. Earth's tilt, currently around 23.5 degrees, is the quiet hero of habitability. Steady, predictable, and just rebellious enough to keep life interesting. That tilt is the reason we have spring blossoms, summer beaches, autumn leaves, and winter sweaters. When Earth leans toward the sun, one hemisphere basks in warmth, while the other cools in shadow. 6 months later, they swap roles. This gentle pendulum of light and temperature sets the rhythm for ecosystems, migrations, and agriculture. Without it, the equator would bake eternally, while the poles froze solid. In essence, the tilt turns sunlight into a shared resource, spreading energy around the planet in manageable doses. But the real marvel isn't that Earth is tilted, it's that the tilt stays so steady. Over long timescales, it does shift slightly, oscillating between about 22 and 24 degrees in a slow, graceful wobble that takes tens of thousands of years. These subtle variations, known as Milankovitch cycles, do influence the timing of ice ages, but they're nothing compared to the wild swings of our red neighbor. Mars's tilt doesn't just wobble, it whirls. Mars currently tilts at about 25 degrees, almost identical to Earth's. But that's pure coincidence. Without a large moon to act as a stabilizing anchor, Mars's axis is at the mercy of gravitational tugs from other planets, especially Jupiter, the solar system's heavyweight troublemaker. Over millions of years, Mars's tilt has swung anywhere from a modest 15 degrees to a dramatic 60 or more. Imagine going from Earth-like seasons to one where the poles face the sun directly for half the year, then freeze in total darkness for the other half. It's a planetary identity crisis on repeat. This chaotic wobble has turned Mars's climate into an unpredictable mess. When the tilt increases, the poles receive more sunlight, causing polar ice caps to melt and release carbon dioxide. That thickens the atmosphere slightly, warming the planet. When the tilt decreases again, the opposite happens. Temperatures plummet, carbon dioxide freezes out of the air, and the planet's thin atmosphere becomes even thinner. Mars's weather doesn't just change year to year. It transforms epoch to epoch, rewriting its climate script every few million years. Evidence of these cycles lies etched into the Martian landscape. Layers of ice and dust in its polar caps form like the rings of a tree, recording each major tilt shift. Satellites have even spotted ancient glacial deposits at latitudes where ice couldn't exist today, suggesting that in past high tilt periods, snow and frost once reached the equator. Mars has essentially moved its ice caps around the planet like luggage, never quite sure where to settle. If there were ever a planet in need of a cosmic therapist, it's Mars. Earth, in contrast, owes its calm demeanor to its oversized companion, the Moon. When a Mars-sized object slammed into early Earth billions of years ago, In the same impact that created the moon, the debris that formed our satellite became a stabilizing hand on the planet's shoulder. The moon's gravitational pull acts like a gyroscope, keeping Earth's axis from spinning out of control. Without it, our tilt might have fluctuated as wildly as Mars's, and the resulting climate chaos could have made long-term life impossible. The moon, it turns out, doesn't just light up our night sky, it keeps our seasons from turning into existential roulette. The connection between axial stability and habitability can't be overstated. Life depends on consistency. Plants need predictable sunlight to evolve photosynthesis strategies. Animals need seasonal cues for migration and breeding. Even the timing of ice ages has shaped human history, nudging migrations, agriculture, and civilization itself. A world with random tilt swings would offer none of that. On such a planet, ecosystems couldn't find rhythm, evolution couldn't plan ahead, and any spark of complexity would be constantly snuffed out by abrupt climate upheaval. Mars shows us what that instability looks like in slow motion. Its climate history is a patchwork of frozen eras punctuated by fleeting thaws. Sometimes the tilt brought temporary warmth, allowing ice to melt and carve channels across the surface. Then, the planet leaned back the other way, temperatures dropped, and everything froze again. Each thaw was like a false spring, a brief moment of promise before the deep cold returned. Over billions of years, that instability helped drain Mars of its last remaining chances at habitability. The fluctuating tilt caused atmospheric gases to condense and escape, surface ice to migrate and vanish, and potential habitats to form and then die. It's a story of almosts. A planet that kept resetting itself before life could get comfortable. On Earth, stability has given evolution time to build complexity layer by layer. From coral reefs to rainforests, life has adapted to the planet's gentle seasonal beat. Even when Earth's tilt shifts slightly, ecosystems adjust rather than collapse. It's a subtle reminder that our planet's most important life support system isn't just oxygen, water, or warmth, it's predictability. Imagine if tomorrow our tilt suddenly jumped to 40 degrees. Summers in the tropics would become unbearable furnaces. Winters in the mid-latitudes would plunge into deep freeze. Ice caps would melt and then refreeze unpredictably. Coastlines would drown and retreat, and the stability that agriculture and civilization depend on would vanish. Earth would survive physically, but our way of life wouldn't recognize it. In cosmic terms, that's what Mars has endured again and again. So yes, Earth's tilt may seem like a small detail, just a few degrees of lean, but it's one of the reasons you can plan a vacation 6 months from now without wondering if your hemisphere will still have sunlight. The moon's quiet tug keeps our world poised, our climate balanced, and our seasons reliable. Mars, poor Mars, spins on in its eternal wobble, its climate rewriting itself like a forgetful storyteller. It once had the potential for stability, warmth, maybe even rain, but without an anchor, it tipped into chaos. Earth, meanwhile, found equilibrium in imperfection. Just enough tilt for variety, just enough steadiness for survival. In the grand ballet of the solar system, a steady spin might not seem glamorous, but it's the secret to life's long run. Mars dances wildly and burns out. Earth keeps its tempo, and the show goes on. Earth's moon does more than make tides and romance poetry. It stabilizes our rotation. Without it, Earth might have tumbled chaotically like Mars, which only has two potato-shaped moonlets that can't even keep their orbits together. Our moon is basically the planet's emotional support satellite. The moon is such a familiar sight that it's easy to forget how outrageously special it is. Look up on a clear night and you'll see what seems like a simple companion, a glowing disk hanging in the dark. But that silent orb isn't just a pretty backdrop for lovers and werewolves. It's the reason Earth is still a balanced, stable, and life-sustaining world. Without it, our planet might spin, wobble, and tilt itself into unrecognizability. The moon isn't just a cosmic accessory, it's Earth's co-pilot. The story of how it came to be is one of the most dramatic events in planetary history. Around 4.5 billion years ago, when Earth was still young and molten, a rogue world the size of Mars, named Theia, smashed into it with unimaginable force. The impact melted much of Earth's crust and blasted a vast plume of molten debris into orbit. Over time, gravity pulled that debris together, forming a glowing, spinning sphere that cooled into the moon. So, the very satellite that now watches over our nights was born out of cosmic violence. You could say the moon is Earth's greatest souvenir from a near-death experience. But this catastrophic beginning was also a blessing. That impact didn't just create the moon, it reshaped Earth itself. The collision tilted Earth's axis to its present angle, setting the stage for seasons. It sped up the planet's rotation, giving us the first 24-hour day. And most importantly, the newborn moon began its quiet job as a stabilizer. Like a celestial hand holding Earth steady, it prevents our planet's tilt from wobbling wildly over time. Without it, Earth's axis could vary as much as Mars's does, flipping our climate between extremes. The moon, in essence, turned chaos into choreography. Mars, in comparison, got the short end of the satellite stick. Its two tiny moons, Phobos and Deimos, are lumpy rocks, more captured asteroids than true moons. Phobos is so close to Mars that it orbits faster than the planet rotates, slowly spiraling inward and doomed to crash or break apart in about 50 million years. Deimos drifts outward like it's trying to quit the family chat. Neither has the mass or distance to stabilize Mars's rotation. They tug a little, but not enough to make a difference. The result? Mars's axis wobbles dramatically, sending its poles and climate swinging in unpredictable cycles. Earth's moon, by contrast, keeps our world's head held high. One of the moon's most obvious influences is the tides. The gravitational pull between Earth and the moon stretches our oceans, creating rhythmic bulges that rise and fall as the planet rotates. These tides might seem like small-scale motion, but they've shaped coastlines, weather patterns, and even life itself. Early in Earth's history, tidal zones, where the ocean met the land, were likely crucibles for evolution. The constant ebb and flow mixed chemicals, concentrated nutrients, and provided the perfect testing ground for early life to inch its way onto land. Without tides, evolution might have stayed stuck in the sea. But the moon's gravitational partnership does more than move water. It also slows down Earth's rotation, very slowly, about 1.5 milliseconds per century. Billions of years ago, A day on Earth lasted only 6 hours. As the moon pulled on the planet, the friction between ocean tides and the seafloor acted like a brake, transferring energy from Earth's spin to the moon's orbit. That's why the moon is slowly drifting away, about 4 centimeters per year. Every time you look at the moon, it's a little farther than the last time you checked. One day, eons from now, it'll be too far to cause total solar eclipses. Future civilizations, if any remain, will have to make do with partial ones. Despite that slow retreat, the moon continues to do its job as our planetary stabilizer. It keeps Earth's tilt within a narrow range, ensuring the seasons stay predictable enough for life to adapt. This stability has allowed ecosystems to evolve around reliable temperature and sunlight patterns. Crops can grow, migrations can repeat, and life's rhythms can sync with the steady beat of the moon's orbit. Even human biology seems to have tuned itself, however subtly, to lunar cycles, an ancient echo of our connection to the sky. Mars's lack of such a stabilizer has had deep consequences. With no larger moon to keep it in check, its axial tilt can swing by tens of degrees over geological timescales. This means that what is now a frozen pole could once have basked in direct sunlight, melting its ice caps and releasing bursts of carbon dioxide into the air. Then, as the tilt shifted again, those same regions would freeze over. It's climate whiplash on a planetary scale. No biosphere could thrive in such unpredictable conditions. The absence of a big moon didn't just change Mars's nights, it changed its fate. The moon's influence reaches even into the psychological realm of humanity. It's been a companion in myth, navigation, and timekeeping since the dawn of civilization. Ancient calendars followed its phases. Poets worshipped its glow. Explorers used it as a guide. In a way, the moon is the first cosmic object humanity ever truly understood, a reminder that we're part of a larger system, not just a lonely rock adrift in space, and that familiarity hides its quiet, practical magic. Every gentle tide, every steady season, every sunrise predictable enough to plan a harvest owes something to that pale satellite. It's easy to imagine alternate versions of Earth, ones that spun without a moon to steady them. Perhaps they'd wobble through wild climate cycles, their seas sloshing irregularly, their winds ungovernable. Maybe life would still arise, but it would struggle against constant upheaval. Intelligent species might never emerge, their world too unstable to nurture long-term civilizations. Stability, after all, is the unsung hero of evolution. The moon is a reminder that luck and disaster often come from the same place. A collision that should have destroyed our planet instead gave us balance, tides, and poetry. Mars never had such luck. Its moons are mere footnotes, tumbling through unstable orbits, powerless to calm their parent world's restless spin. So, the next time you see the moon rising over the horizon, glowing softly against the dark, remember that light is more than beauty. It's the steady heartbeat of our planet's rhythm. It's gravity made gentle, chaos made calm. Earth is a world that learned to dance because it found the perfect partner. Mars? It's still trying to find its footing in the dark. Once the conditions were right, life popped up on Earth faster than a cat finding an empty box. Mars may have had the ingredients, but without liquid water and atmosphere, the recipe failed. Somewhere out there, ancient Martian microbes are probably still waiting for their sequel. If the history of the universe were a 24-hour day, Earth would have formed around 4 a.m., and humans wouldn't appear until the last few seconds before midnight. But the real plot twist happened much earlier, around sunrise, when life itself entered the scene. Barely a few 100 million years after Earth cooled enough for oceans to form, the first living organisms appeared. That's astonishingly fast. The universe didn't even finish its morning coffee before Earth started experimenting with biology. We still don't know exactly how life began, but the ingredients were certainly there. The early Earth was a chemical playground. Oceans rich in minerals, volcanic gases thick with carbon compounds, lightning striking through the atmosphere like a cosmic mixing spoon. In that stew of chemistry, something extraordinary happened. Simple molecules learned how to copy themselves. From there, evolution took over, and suddenly, Earth wasn't just a rock anymore. It was alive. Mars likely had similar conditions around the same time. It had water, heat, carbon dioxide, and the right mix of elements. The two planets were like twins attending the same cosmic chemistry class. The difference is that Earth had more time and stability to let life grow up. Mars, smaller and quicker to cool, lost its warm atmosphere and liquid oceans before anything complex could evolve. If life ever appeared there, it might have been short-lived, microscopic, and buried, snuffed out before it had a chance to write its story. On Earth, once life took hold, it proved almost impossible to get rid of. Microbes colonized every environment, from scalding hydrothermal vents to freezing polar ice. They invented new ways to eat, breathe, and multiply. Some used sunlight, others consumed sulfur or iron. Life diversified like a cosmic startup boom. Organisms trying every possible business model until something worked. The fact that life appeared so quickly and adapted so relentlessly suggests that the universe might not be stingy with it. If you give nature the right conditions, life doesn't need much encouragement. It just happens. That's what makes Mars so tantalizing. Scientists have found traces of organic molecules in its rocks, carbon-based compounds that are the raw materials of life. They've discovered ancient riverbeds and minerals that only form in the presence of water. The puzzle pieces are there. They just never assembled into the full picture. It's as if Mars had all the ingredients laid out on the counter but never turned on the oven. Still, the possibility that Mars once hosted life refuses to die. Some researchers believe that simple microbes might still exist beneath its surface, protected from radiation and freezing temperatures. Deep underground, where geothermal heat lingers and briny water might remain liquid, there could be pockets of habitability. If those microbes are real, they would be the oldest and loneliest organisms in the solar system, life that refused to quit even when the planet around it did. Ironically, Mars might owe its best chance for life not to itself, but to Earth. During the heavy bombardment era, massive impacts on our planet could have ejected chunks of rock into space, rocks carrying microbial stowaways. Some of those fragments could have landed on Mars. The reverse is also true. Pieces of Mars have made their way to Earth. We've found them as meteorites, and inside them, scientists have spotted odd microscopic structures that some have argued look biological. It's not proof, but it's enough to keep the question open. Could life have jumped between worlds? If so, we might share an ancient family tree with a planet that's now barren. The search for Martian life has become one of humanity's most compelling scientific quests. Every rover, from Curiosity to Perseverance, carries tools designed to sniff out evidence of past biology. They look for signs of ancient microbial mats, chemical imbalances, or fossils too small for the naked eye. Each discovery adds another breadcrumb to the trail. The day we find proof, if it ever comes, will be the day Earth's story stops being unique. But what makes Earth's success so striking isn't just that life appeared, it's that it stayed. Our planet nurtured it through asteroid impacts, volcanic winters, and ice ages. Life survived every catastrophe by adapting, hiding, or reinventing itself. Bacteria learned to photosynthesize, animals learned to breathe oxygen, and humans eventually learned to question it all. Life here isn't fragile. It's annoyingly persistent. It spreads into every niche, from boiling acid pools to the inside of your refrigerator. That persistence raises an uncomfortable question. If life began so quickly on Earth, why haven't we found it elsewhere? Maybe Mars is proof that starting life is easy, but keeping it alive is hard. Maybe the difference between a living planet and a dead one is just a few strokes of luck. A thicker atmosphere, a magnetic shield, a stabilizing moon. Earth had all three. Mars had none. And yet, Mars remains the best candidate for a second Genesis in our cosmic neighborhood. Venus is too hot, the outer moons are too cold, but Mars is just right in the middle. It's the Goldilocks planet that didn't make it. The one that almost joined the party but had to leave early. If we do find life there, even fossilized remnants, it would rewrite our understanding of existence. Because if life arose twice in the same solar system, it's probably everywhere. The universe wouldn't be a lonely void anymore. It would be an endless symphony of biology. For now, though, Earth stands alone as the only place where life not only emerged, but thrived. It's a reminder of how thin the line is between barren and blooming. Every breath we take, every tree we see, every fish, bird, and bacterium, all of it exists because a small planet managed to hold on to its warmth, water, and luck. Life didn't just find a way here, it found a home. Mars, in its quiet solitude, remains the question mark in that story. Maybe its microbes are still sleeping beneath the dust, dreaming of oceans long gone. Maybe they're extinct, their traces locked in stone. Either way, Mars reminds us that life isn't guaranteed. It's a spark that can ignite quickly but vanish just as fast. Earth was the planet that kept the flame alive. Mars was the one that let it flicker out. But who knows? The universe has a habit of surprising us. Somewhere in the red dust, under layers of ice or rock, that ancient spark might still be waiting, not for us, but for a chance to begin again. Mars's thin air lets dust run wild, creating storms that can engulf the whole planet for weeks. Earth's atmosphere, thick and wet, keeps its dust in check. The Martian surface looks like a place that hasn't been dusted since the dinosaurs. If dinosaurs had ever lived there. Mars is the universe's greatest hoarder of dust. It doesn't just collect it, it celebrates it. The entire planet is coated in a fine layer of reddish powder that's been accumulating for billions of years. Every gust of wind lifts it, every sunset glows through it, and every rover that lands there ends up looking like it's been through a cosmic sandblaster. On Earth, a good rainstorm clears the air. On Mars, there hasn't been a proper cleaning in eons. The problem starts with the atmosphere, or rather, the lack of one. Mars's air is less than 1% as dense as Earth's, made mostly of carbon dioxide with only traces of water vapor. You'd think such thin air wouldn't be able to move much around, but that's where Mars gets sneaky. Its low density means dust grains don't fall easily. Once lifted by even a small breeze, they can stay suspended for hours, days, or sometimes weeks. It's like glitter at a kid's birthday party. Once it's in the air, good luck ever getting rid of it. The source of all that dust is the planet itself. Mars's surface is covered in a layer of fine, iron-rich sediment created by billions of years of erosion, impact cratering, and chemical weathering. Without rain to wash it away, or vegetation to hold it down, the dust just builds up. Every micrometeorite strike, every temperature swing, every whisper of wind grinds rocks into smaller and smaller particles until the whole planet is wrapped in its own powdered remains. The very thing that gives Mars its iconic red color is also what makes it a nightmare for machines and explorers alike. When the wind picks up, Mars transforms from a quiet desert into a roaring sea of airborne grit. Local dust devils, mini tornadoes of wind and sand, dance across the plains, some stretching miles high. They can reach speeds of over 100 kilometers per hour, fast enough to lift fine dust but too weak to move larger rocks. These devils leave dark, looping trails on the surface that fade over time, tracing the restless behavior of a planet that never truly sleeps. But the real showstoppers are the global dust storms. Every few years, Mars experiences a meteorological meltdown where storms merge and grow until they cover the entire planet. One moment, the sky is pink. The next, it's an impenetrable orange haze. Sunlight dims to a faint glow, temperatures drop, and solar-powered rovers go silent, starved of energy. The storms can last for weeks or months, choking the atmosphere with dust so fine it behaves more like smoke than sand. For humans or machines, it's the equivalent of being stuck in a planetary-sized vacuum cleaner bag. The most famous of these storms occurred in 2018, when a massive global event smothered Mars for 3 months. It was so intense that NASA's Opportunity rover, which had been exploring the planet for 14 years, lost contact. Its solar panels were coated with dust, and the faint sunlight that reached the surface wasn't enough to recharge its batteries. Opportunity's final message, "My battery is low and it's getting dark," became an emotional epitaph for a world where even robots can't outrun the weather. On Earth, dust plays a different role. Our atmosphere is thick with moisture, and our planet's surface is constantly reshaped by wind, rain, and vegetation. When dust rises, it's usually short-lived, washed out by rain or trapped by plant roots. Still, Earth has its dusty moments. The Sahara's vast plumes that drift across the Atlantic, nourishing the Amazon rainforest with nutrients, or the swirling brown clouds of the Gobi Desert that reach as far as Japan. But even at their worst, Earth's dust storms are amateurs compared to Mars's endless haze. There's also a strange beauty to Martian dust. It paints the sky in shades of butterscotch and salmon pink. It scatters sunlight in a way that makes sunsets on Mars appear blue, while daytime skies glow red. The dust acts like a giant color filter, changing the planet's mood from hour to hour. It's poetry in particles. Gritty, dangerous poetry, but still poetry. However, that same dust poses one of the greatest challenges to future human explorers. The particles are not just fine. They're sharp, electrostatically charged, and cling to everything. They can infiltrate machinery, jam joints, and scratch delicate surfaces. Worse, the dust contains toxic chemicals called perchlorates, which are hazardous to humans. Breathe too much in, and you're in for a bad day, possibly a short one. Any future Martian base will need serious dust-proofing, not just to keep the equipment clean, but to keep the astronauts alive. Scientists suspect that dust may even influence the planet's temperature and climate cycles. When storms lift massive amounts of particles high into the atmosphere, they absorb and scatter sunlight, altering the planet's energy balance. This can trigger feedback loops, warming certain regions, cooling others, and redistributing air currents. On a planet without oceans or a dense atmosphere to stabilize things, dust is the climate. It's both the weatherman and the storm. Yet for all its chaos, the dust also preserves Mars's history. Beneath that powdery blanket lie clues to its wetter past, fossilized riverbeds, ancient lake sediments, and perhaps even traces of microbial life. Every gust that erases old tracks also reveals new secrets. Mars is a planet constantly rewriting its own surface, layer by layer, in rust-red script. In a way, the endless dust is symbolic. It's the residue of a world that once moved with rivers and rain, but now only whispers with wind. Each storm is Mars remembering its past, stirring up the ghosts of its ancient oceans, letting them drift once more across the plains. Earth may have water to wash its face clean, but Mars keeps its memories close, coated in dust. So when we finally set foot there, humanity will step into a world that hasn't been touched or tidied in billions of years. Every footprint will stay. Every rover track will linger. Mars never truly forgets. It just buries its story slowly, grain by grain, beneath the dust that never settles. There were times Earth almost blew it. Massive volcanic winters, asteroid impacts, even near runaway greenhouse events. Each time, the planet teetered on the brink of becoming Mars 2.0. But balance always found a way to return, like the universe hitting undo just in time. Earth today looks calm and composed, a blue marble serenely spinning in space. But don't be fooled. Our planet has flirted with disaster more times than we can count. If the story of life on Earth were a movie, it wouldn't be a gentle nature documentary. It'd be an action thriller with explosions, comebacks, and an unbelievable number of close calls. Each catastrophe could have ended the story entirely, but somehow Earth kept rolling the credits back. Let's start with one of the most terrifying plot twists: asteroid impacts. 66 million years ago, a 10-kilometer-wide space rock slammed into what's now Mexico's Yucatan Peninsula. The impact was instantaneous apocalypse. The force was equivalent to billions of atomic bombs, vaporizing everything nearby and throwing enough debris into the sky to block sunlight for years. Forests burned, oceans boiled, and the global temperature dropped so fast that 3/4 of Earth's species, including the dinosaurs, didn't make it. It's easy to think of that event as a total wipeout, but in a strange way, it was also a reset button. Mammals, which had been scurrying in the shadows for millions of years, took their chance to rise. The extinction cleared the stage for new life, including us. It was nature's harsh way of saying, next. Still, one can't ignore how close we came to joining Mars as another lifeless rock. A few kilometers difference in trajectory, and Earth's recovery might not have happened at all. That wasn't even the biggest near miss. Go back further, to about 25 billion years ago, and Earth faced a slow-motion crisis called a snowball event. Global ice spread across the surface until even the equator froze. The oceans turned into slushy prisons, trapping sunlight beneath reflective white ice. Volcanoes kept spewing carbon dioxide, but with so little liquid water to absorb it, the greenhouse gases eventually built up enough to melt the planet out of its deep freeze. Had that balance tipped even slightly further, the planet could have stayed frozen indefinitely. Earth would have been a white version of Mars. Silent, glacial, and done. Then there were the opposite disasters, times when the planet nearly cooked itself. Around 252 million years ago, in what's known as the Permian-Triassic extinction, massive volcanic eruptions in Siberia released vast quantities of carbon dioxide and methane. The temperature soared, oceans acidified, and over 90% of all species perished. Imagine a world where even the insects are having a bad time. That was the Permian. It's often called the Great Dying, and it remains the closest Earth has ever come to turning into a sauna planet. It took millions of years for ecosystems to crawl back from that edge. Volcanoes have always been double-edged swords for Earth, creators and destroyers rolled into one. They replenish the atmosphere and build continents, but when they go all in, they can darken skies and choke ecosystems. Around 74,000 years ago, the eruption of Mount Toba in Indonesia nearly triggered another mass extinction. Ash filled the stratosphere, blocking sunlight and plunging the world into a volcanic winter. Genetic evidence suggests that humanity barely scraped through, with perhaps only a few thousand individuals surviving to repopulate the planet. The fact that you're reading this right now means your ancestors survived one of the bleakest bottlenecks in human history. Congratulations! You come from a long line of near misses. And then there's the one we might still be flirting with, the runaway greenhouse effect. Venus, our planetary neighbor, is a grim warning of what happens when a planet loses control of its climate. Billions of years ago, Venus may have had oceans and clouds, but as volcanic activity released carbon dioxide and sunlight heated the surface, water evaporated into the atmosphere. Water vapor is a potent greenhouse gas, so temperatures climbed higher, triggering more evaporation. The cycle spiraled until the oceans boiled away completely, leaving Venus an inferno wrapped in sulfuric acid clouds. Earth has danced dangerously close to that edge a few times. During the early evolution of life, methane-producing microbes pumped greenhouse gases into the air, heating the planet until oxygen-producing organisms stepped in and cooled things back down. Later, During periods of high volcanic activity, carbon dioxide again surged, and the climate teetered. Each time, natural feedback systems like rock weathering and photosynthesis slowly reeled things in. But the balance is precarious, and we've never been more aware of that than now, as our own species tinkers with the thermostat faster than nature ever has. Cosmic accidents also nearly derailed Earth's story. Massive solar flares have occasionally bombarded the planet, stripping away parts of the upper atmosphere and disrupting magnetic protection. Supernovae exploding nearby could have bathed Earth in deadly radiation. Even subtle orbital shifts have sometimes conspired to freeze or fry our world. The solar system's chaos is always just a few gravitational nudges away from rewriting the script. And yet, through all of it, Earth keeps bouncing back. That resilience isn't luck, it's physics and feedback. The oceans absorb heat and gases, volcanoes recycle elements, and life itself participates in regulating the atmosphere. The biosphere acts as both a beneficiary and a guardian of stability. When things get too cold, respiration and decay release warming gases. When things get too hot, plants pull carbon from the air. It's as if the planet learned, over eons, to heal itself. Mars didn't get those chances. When its volcanoes died, its magnetic field vanished, and its atmosphere slipped away. It lost every natural safety net. Earth, meanwhile, has survived by sheer persistence and a little cosmic luck. Each undue moment was a reminder that stability in the universe is an illusion. What matters is the ability to recover. If you step back and look at our planet's history, you realize how improbable our continuity really is. Earth has been smacked, frozen, fried, and poisoned. And yet, here we are. A planet that refuses to quit. A world that teeters on chaos but always finds its balance again. Maybe that's the secret to life in the cosmos. Not perfection, but resilience. Not eternal calm, but the ability to weather storms. Earth has walked the edge of disaster countless times, and every time it stumbled, it found a way to stand back up. In the grand cosmic story, survival isn't luck. It's the art of not giving up when the universe keeps trying to delete your save file. Mars stands as a cosmic warning label. Handle your planet with care. If we strip away our atmosphere or warm things up too much, we might find ourselves living on the sequel no one asked for. Earth, the dust awakens. But for now, our blue marble spins on, lucky, living, and still just one bad decision away from being very, very red. Mars is a mirror held up to our own fragility. It's what happens when a planet stops being able to take care of itself, or rather, when nature stops giving it the tools to do so. Its valleys are dried-out riverbeds, its mountains are extinct volcanoes, and its skies are the color of faded blood. Once, it might have been beautiful in a familiar way. Wet, warm, perhaps even welcoming. Now it's the ghost of a world that couldn't hold on. And as we look across the gulf of space toward that red desert, we can't help but see the faint outline of what might someday be us. On Earth, we've grown comfortable. We assume our oceans will always lap at our shores. Our air will always be breathable, and our seasons will come right on schedule. But the truth is, Earth's balance is not guaranteed. It's maintained. The forces that make our world livable are constantly at work, adjusting, recycling, and correcting. Our magnetic field deflects the sun's deadly wind. Our volcanoes and oceans regulate carbon dioxide, and our biosphere keeps gases and temperature in harmony. Remove just one of those safety nets, and things can unravel faster than we'd like to believe. Mars reminds us how thin that line really is. Its atmosphere, once thicker, was slowly stripped away until it could no longer trap warmth. Its water evaporated, its magnetic field died, and the planet froze beneath a red sky. What's left is an image of silence. No wind strong enough to whisper, no rain to cleanse, no rivers to flow. Just dust, ice, and regret. If Earth systems ever stopped working in unison, we'd follow the same trajectory, only slower and with more drama. We've already proven capable of throwing wrenches into our planet's delicate machinery. Our factories, engines, and industries have pumped billions of tons of greenhouse gases into the air, nudging the thermostat upward. Forests that once absorbed carbon are shrinking. Ice that once reflected sunlight is melting. It's easy to think we're far from becoming Mars, but the transformation doesn't happen overnight. It happens by degrees, both literal and metaphorical. The red planet didn't die in a day. It faded, one lost molecule of atmosphere at a time. In a way, Mars is a planetary obituary written in dust. It's the story of what happens when feedback loops turn vicious instead of virtuous, when heat escapes faster than it's replaced, when air bleeds away into space, when the weather stops cycling and simply stops. The very things that once made it habitable became the instruments of its undoing. It's a reminder that a planet's survival depends not on strength, but on balance. The contrast between Mars and our Earth is cosmic irony. One glows blue with abundance. The other glows red with warning. The two worlds are neighbors, siblings even, born from the same nebula, made of the same materials. Yet one hums with oceans and life, while the other lies cold and silent. If that doesn't make us feel small and lucky, nothing will. But Mars's story isn't just tragedy, it's instruction. It teaches us what can go wrong and, more importantly, what must never go wrong here. Losing our atmosphere wouldn't take a cosmic event. It could happen slowly, through mismanagement. If we warm the planet enough to melt the polar ice caps, we could weaken ocean currents, disrupt weather patterns, and release methane locked in permafrost, accelerating warming even further. If deforestation and pollution continue unchecked, we could thin the air of oxygen and fill it with toxins. We may not become Mars exactly, but we could make Earth a poor imitation. The irony is that while we're busy breaking our own climate system, we're also trying to terraform Mars, to make it more like Earth. Scientists dream of releasing carbon dioxide trapped in Martian ice to warm the planet and create an atmosphere thick enough to breathe. It's poetic, really, trying to wake a dead world while putting our living one to sleep. But Mars also offers hope. It reminds us of what resilience looks like, even in stillness. The planet may be frozen and dry, but it still holds its history, written in its rocks and dust. It still orbits the same sun, still reflects light across the void. In its quiet way, it endures. And that endurance should inspire us, not to repeat its mistakes, but to learn from them. We are, in a sense, the stewards of Earth's experiment. Life has handed us the keys to a planet that has survived billions of years of chaos. But unlike Mars, we have the awareness to understand our influence. We can measure the damage, foresee the consequences, and choose to act differently. Mars can't fix itself. We can. Look up at the night sky, and you'll see Mars shining faintly red, a distant ember among the stars. That glow isn't just light. It's a cautionary reflection. It's the whisper of a planet that once had a chance and lost it. It's the universe's way of saying, don't let this happen to you. Because, make no mistake, the conditions that keep Earth alive are temporary, maintained by cooperation between geology, biology, and time. We're part of that equation now, whether we like it or not. Every action we take, every forest cut, every ton of carbon burned, is a hand nudging the balance. We can push toward blue, or we can drift toward red. For now, the blue still wins. Our oceans still glisten. Our skies still shelter us, and the planet still hums with life. But Mars is out there, watching, a cosmic ghost story painted in iron oxide. Its silence reminds us that survival isn't owed, it's earned, and it must be renewed every generation. So yes, Mars is beautiful, but it's the kind of beauty that should make you shiver. It's the haunting reminder that worlds can fail, and it's the reason we should cherish every drop of rain, every gust of wind, every green leaf trembling in sunlight. Because if we ever forget how to take care of this miracle we live on, Mars won't have to say a word. We'll already know how the story ends.